Good evening, all, and welcome to our program for the Rochester chapter of IS&T. This is the first time we've met in person in 3 years, partially due to the nudging of our speaker, but also it's spring and it seems like it's a good time to get out and do usual things. I am David Odgers, the president and vice president of programs. Bruce is going to introduce our speaker. So thank you.
Okay, I've got the good fortune of introducing Majid and Prasanna. Majid's, you mostly know Majid, so I'll leave that out. And Prasanna is a nearing the end PhD student working with Majid. And so I will get out of the way and enjoy the presentation.
Thank you very much, Bruce. Thank you all, by the way, and thank you for IS&T for inviting me tonight. It's a great honor to be here. So let me start with a story. Everyone has heard of Warren Buffett and Charlie Munger. Charlie Munger, during one of these Berkshire Hathaway annual meetings, related this story, which might be apocryphal, but this is about Max Planck, who won the Nobel Prize in 1918 because of his quantum theory. And Max was asked to make presentations at all of these different universities, some of which were quite remote. And, you know, he had to drive with his chauffeur, go to these places. This is 1918, and deliver all of these speeches. So after doing about 35 of these, one night they were driving to this remote place near Munich to a university, and he was very tired. So the chauffeur turns around and says, "Boss, you know, I've listened to you deliver this talk more than 30 times. And I know this inside and out. And I know what kind of questions people are going to ask. So let me do the presentation. They don't know who you are or what you look like or what I look like. And I bet you they can't tell the difference." And Max thinks and says, "You know, that sounds like a good idea. Why don't we do that?" So the chauffeur delivers the talk. It's a great talk. You know, he's listened to it 30 times. And first few questions are kind of routine questions. You know, how did you come up with this idea or this and that? And he can answer them. Until one person, amazingly, asks a very detailed technical question that the chauffeur, of course, does not know. So he thinks about it and says, "This is such an elementary question that even my chauffeur can answer that. So I'm going to defer it to my chauffeur." So when Charlie Munger uses that story, he's essentially referring to the fact that a lot of people who make financial advice these days or talk about these things, they really only have chauffeur knowledge of what they're talking about. The reason that I share this story with you is because a good part of my talk, which has the more interesting results tonight, is going to be about deep learning. And I want to tell you that I only have a chauffeur knowledge of deep learning. The real Max Planck is sitting over there. And if you have questions, I'm going to defer them to Max to answer them, because I will not be able to answer questions at that level of depth. But with that said, let's talk about super resolution tonight. So what is image resolution? Resolution can mean different things for different imaging applications, right? We mainly mean spatial resolution in today's presentation, which is essentially the pixel density, if you wish, in an image, usually measured as pixels per unit area, but there's also tonal resolution, temporal resolution, and spectral resolution. But when we talk about super resolution tonight, we really are referring to spatial resolution. And we essentially want to be able to reconstruct an image with number of pixels or resolution higher than what the camera has captured it with. Okay, so in order to give you a feel for what, because we're going to be talking about these factors, 2x, you know, improvement, 4x improvement, 8x improvement. Let's see visually or perceptually what they mean. So this is, of course, a very low resolution image intentionally so that everyone can see it, even my eyes. And this is that same image with twice as much resolution, which will have 4 times as many pixels. Okay, and this is that same image with 4x higher resolution. And for those who were around during the VHS era, a 2x increase in resolution is like going from VHS to DVD, or going from DVD to HD, or going from HD to 4K. Okay? And that is exactly what the perception of an improvement of 2x in resolution would look like. I'm going to show you a video that you could download from YouTube. It's part of this movie, The Blade Runner, which was made in 1982. Okay, and a lot of people will consider that kind of the birth of super resolution. Of course, none of these techniques were available at the time, but we're going to go to that video, and I'm going to try to play it. Now, here is the problem. Because we don't have audio, the audio is going to come out of the computer, and it's not going to be that loud. So there are parts of it that I just transcribed here, you will see. But it's about a minute, and it's a fun video to watch, because that kind of tells you what Hollywood thought of super resolution at the time. You probably can't hear some of the noise here, but. So this shows Harrison Ford trying to spot some object that he has seen in that picture. And the contrast may not look that good, but you know, you can download it from here. So it's actually fun to watch. If we had audio, it would have been better, but. So this is what would have been a perfect kind of user interface doing super resolution at the time. I think from now on, you could just read on. Enhance 34 to 36. Pan right and pull back. Wonder if that is possible today. And that's the story. So this was done in 1982. Okay. Now we are 40 years later. And it happened that 2 years after this movie, there was the first breakthrough. And I'm kind of trying to give you the timeline here. So this breakthrough was when Tsai and Huang made this computational super resolution. And I will tell you what computational super resolution is. I come from a traditional signal processing background, and that's my area of expertise. But then all of the exciting, fun results that you will see tonight are from the deep learning and you know, the machine learning kind of community. But let's review that first. Then 2 decades later, there was the first paper that was published called Face Hallucination. It kind of shows how you could get a low resolution face and make it higher resolution. But then at that time, around 2004, which is if you take from Blade Runner to now 40 years, halfway in between, around 2004, there was a seminal paper, which we will talk about, that practically was the state of the art and still is, of what we call computational super resolution. And I will explain what that means in a moment. Then things kind of stalled until about 10 years later in CVPR, which is the conference for computer vision and pattern recognition in 2017, there was this paper that was presented, which I will show you some pictures of, about GAN. It's called super resolution SR GAN, which is generative adversarial networks. Okay, and this is what this is kind of the state of the art at the time. This is what it looked like, right? So you will have a low resolution image like that, and the GAN could give you a picture like that. Or you will start with a low resolution image like this, and the GAN will give you a picture like that. Well, when we made the presentation, Prasanna and I, this presentation actually was made about 2 years ago as part of the seminar series for the Center for Imaging Science at RIT. There are some papers after this, which I will talk about in 2020. But then this presentation was made in 2021. And when Roger asked me to do the presentation here, Prasanna updated, and he will do that at the end, by about 6 or 7 slides, the latest stuff, which was just published a few months ago. And then you will see that, which is not here, but is in his presentation. So let's start with thinking of super resolution as really being divided into 2 kinds of approaches. The traditional signal processing approach, okay, which I will explain what it is, and we call it the computational approach because a lot of people will look at it that way. Not that the other one does not involve computations, but it's just the nickname that we use for that. And then we will talk about the deep learning approach, which is all based on neural networks and training them and so on. Okay, so start with what super resolution again is. Super resolution refers to obtaining an image at a resolution higher than that of the camera sensor. We started our presentation with that. And there are 2 ways of doing computational super resolution. Okay, one is you have a picture. Let's say you grab a picture off the internet. And then you say, okay, can I make the resolution of this picture higher? Or your camera captures a picture and you wonder, can I make the resolution of this picture higher? Doing the computational approach, that problem actually is very difficult. Okay? And the way that it's done traditionally is that you usually have a video or you have a sequence of images, and then you take one frame of that, and then you use the knowledge that is in that frame and the knowledge, they're all low resolution frames, okay? But somehow you fuse the knowledge of all of these low resolution frames into a single frame that is higher resolution, okay? That kind of computational approach had a lot of traction, okay? And that's using a sequence of low resolution frames. Let me give you an example. I worked at Kodak for 33 years. Back then, we actually worked with this company called Motion DSP. So all of these things that I'm showing you are not really more academic. They're actually pretty practical. Motion DSP had this, this is again circa 2005, 2004. They had this algorithm that will take these 4 pictures that were taken as part of a low resolution video and will fuse them together to create a higher resolution image. And as you could see, you could actually read the text here, which you couldn't do in the other frames. There are many examples of that, but what's the principle, okay? Without getting into too much detail, let's just look at it from a viewpoint that will be tangible and will make sense to all of us. So imagine that we wanted to capture a higher resolution. I'm really here only talking about a 2x change in resolution, okay? Just makes things simpler. So if I captured the high resolution image, I will have a pixel value at each one of these locations. That will be the high resolution image that I want. But because of my sensor limitations or whatever other issues, I can only capture the image at half the resolution, okay? But now imagine that I had this controlled environment where I could take my camera, okay? And everybody was still, there was no movement or anything, and I will move it exactly by half a pixel to this, and then I will capture that image again. This is another low resolution image, right? And then I will move my camera. And by the way, there are a lot of labs that actually did that, okay? And then you will move the camera down and you will capture, again, this picture. And you will do the same and you will capture this picture. So now you have 4 lower resolution pictures, right? And if you combine them all together, you will have the high resolution image, right? In principle, it's not that difficult, right? But let's see what happens in practice. What happens in practice is that the camera shakes, objects move, you zoom or pan or whatever, right? And there's a lot of noise. So what happens in practice is that you may capture your first image like that. Let's use that as a reference. But your second image might be like that. And that's if you're lucky. And your third image might be like that. And your fourth image might be like that, right? So now if you want to reconstruct that higher resolution image, let's say you want to know what the value of the image is at that pixel, okay? If you knew exactly what all of the transformations were, if you knew what the motion was, then you can say this pixel is a value that can be derived from its nearest neighbors, okay? And that is the computational super resolution. So in order to be able to do that, what you need to know is, first of all, you need to model all of these image captures. And you have to have a robust way of fusing them together, combining them together, modeling them, so that you can get a reliable value or calculate that at that particular location. That's why this is called the computational approach, okay? So again, I use that as an example, but if you wanted to find this, you see this is a near neighbor there. These two are near neighbors, and there should be a rule of combining them in a way that you will get a better or more accurate value for that red pixel than if you just used the four, or the two values that you had captured before. So I really don't like to get into too much math, but I want to at least show you one equation, because no technical presentation is complete without at least having one kind of cool looking complicated equation. So what is happening here is that you have to model the picture, okay, this whole process. So you say, I want to estimate everything that is in red here is something that I don't know and I want to find out. So I have a high resolution image, okay, let's say. And what happens is that there is some kind of a geometric transformation. This is happening all the time. The camera rotates, the scene changes, or I mean, there could be all sorts of geometrical transformations. There is optical blur. My camera is slightly out of focus at times, okay? And there is, but all of those supposedly are known. That's why we put them in blue. And there is downsampling. In this hypothetical example, the downsampling is by a factor of 4. And then on the top of that, there is noise. So then you have the noise added here. So the noise is neither in red nor in blue. So you wonder, what do I mean by that color code there? Well, the thing is, I don't know what noise is, because if I did, I would just subtract it out, right? But on the other hand, I usually know the statistics of the noise, okay? So there is partial knowledge about the noise. That's why the color of this is different than either the red that I don't know at all, or the blue that I do know, okay? And then this is the observation that I make, okay? So essentially, I want to record this, but because of all of these processes that are happening, I actually record that. But then I can make multiple observations, because as I'm pointing the camera at the object, I could take maybe a video at 30 frames per second. So now I can look at 5, 6, 10 frames in order to be able to, I have like 10 of these or 8 of these, and I want to somehow fuse them together to get this thing back, right? So looking at the actual formulation, again, not trying to get into too much math, this observation, which is the only thing you really have, these are usually estimated, okay? But you assume that you either have them or you have to estimate them. Now, the devil is in the details, because estimating these always incurs error, okay? This is what you want to find, and you could model this as one equation where this kind of assembles all of your knowledge of the various parts of the imaging chain that create the actual degradation. So the next, yes.
When you're done with that point, I'd like to ask a question about that equation.
Yeah, of course. Go ahead.
So when DFK
This is the part where I answer the questions. If you have questions on deep learning, then we turn to Max, okay?
So when DFK goes to zero, for example, the fraction limit when anti-aliasing filter, images out of focus, whatever, WK has to go to infinity to recover that. Is that a true statement? So in other words, these methods that you're talking about are limited by the optical. The optical MTF
Yes.
will limit this, and if there's no modulation due to optical MTF, the
Yes.
sensor can't recover it, even though the sensor has infinite support in frequency space.
Yes, that is absolutely correct. There is a paper actually in 2004 by Lin and Sham that they try to model exactly what is the best possible super resolution that you can get when you're diffraction limited. And it turns out that it depends on how well you can estimate all of these parameters. And if you know them perfectly, that number is about 5.6x. And if you don't know them perfectly, it's about 1.6x. So for translational motion. So you can essentially, you can overcome some diffraction limited kind of, issue, but you cannot get infinite super resolution if you had an infinite number of measurements, essentially.
Well, once modulation goes to zero, you're done, right? I mean, if you had an optical lens, a sensor lens system that says, just to pick a number, 100 line pairs per picture height, right? If the optics limits it to that, you can take as many pictures as you want, but you can never get beyond that.
You can actually. That's what I'm trying to say. Okay. Because you could, by displacement of the picture, you get a little bit more new information in every image capture, even though they're all low resolution.
Even if the blur size is bigger.
Exactly. Even if the blur size is bigger, but then you're limited to like 5.6x. And I can actually show you the paper. I have it on my computer, and all the equations that go into that calculation, including the MTF of the camera.
That seems impossible.
Okay. Maybe I misunderstood your question. So this is just, really recapping what I said. Let's look at some pictures, okay? There was a group you remember that picture that I showed you of the 4 pictures that were kind of fused together to create that legible text? That was done by this group in University of California in Santa Cruz, okay? Farsiu is now a professor at Duke University. Milan Far is a Google, he's leading a group that are doing image processing there. And Elad is in Technion University. They're all, heavyweights in this area. And they published this paper in 2004. So you look at the timeline, 1982, we had the Blade Runner. 1984, the first paper came out. 20 years later, this is the state of the art of computational super resolution. And then 20 years it took for all of these deep learning and machine learning to take over. So this paper essentially is and by the way, everything that I say in this presentation, there is a website where you could go, and I'll show you on this one. You can download the actual code, and you can put your own images in there and see to what extent it's improving the resolution of the pictures, okay? So you don't have to believe me for what I say, and you can just really try it on your own. So they developed some papers, here, some techniques. And the main thing to really remember from here is that the big issue is that no matter how many of these captures you have to estimate these parameters. And when you're estimating these parameters, there's usually error in estimating them. And that's why you need regularization. But all of the regularization techniques, they looked at the squared error. And we all know that if you have a bunch of numbers, if you look at their mean, okay, the average value of a bunch of numbers, it minimizes the squared error. But the median of those numbers, okay, which actually minimizes the absolute error, is usually a better representative if you've got error in those numbers, okay? Because the median is very insensitive to the outlier. Write down 5 numbers and then change one of them, make it 10 times bigger, the median doesn't change. But make that number 10 times bigger, the mean changes significantly, right? So the mean essentially is what people refer to as L2 norm in the community, and the median is what they refer to as the L1 norm. So the L1 norm was the kind of regularization that was used in in this particular framework in order to make the sensitivity of the technique to variations in measurements, errors in measurement, essentially, make it less sensitive. So let's look at some images, okay? This is what you start with. And this is, until then, this is the best you could do, which is based on L2 norm, okay? I mean, it's easier said that, oh yeah, it's not that they just make L2 norm, L1 norm. There's a lot of math underlying there, and you know, I'm kind of oversimplifying things a little bit. But then this is what you could get with the state of the art at that time. Now, if you want to be able to create this, you can actually download this code, okay? You can download the MATLAB version of the code, which is, it's not written by the authors, okay? This is some student or whoever that implemented this technique, and Oded Hansen, and you can experiment with your own images. And the website is right here, okay? And here are some images that they also have in their paper. So this is based on 8 frames that are all low resolution. So you're looking at a single frame. This is the best you can do with a single frame. And then if you look at one variation of the technique that they are showing, you know, you could see a lot more detail than you could see before. And then there are 2 actually techniques that they introduced. This is another example. These are particularly important in forensic, for example, applications, so that you could read some of the things that you could not read before. So this was the state of the art in 2004, 2005 timeframe. Okay, and that's what the computational super resolution was able to offer you. And people were pretty happy with that, because if you wanted to print a single frame of some video, okay, and you wanted to print that at a higher resolution so that it was more appealing, you could actually run these algorithms on few frames before and a few frames after, fuse them together, and create a higher resolution image. Okay? But then in 2017, around 2015, the deep learning kind of networks started, sprouting, right? And by 2017, when this paper was published, which I'm about to show you some results, there was a good amount of knowledge on how to take neural networks and train them. You know, neural networks are old. I used to teach them, because I was an adjunct at RIT back in the 80s, okay? But the neural network of the 1980s was like 2 layers, and they were like, 10 nodes connecting to the other 10 nodes, right? But what happened in 2015, circa, was that you got 50 layers, and you got literally millions of connections, and you had these GPUs that were fast enough to be able to train. You had these huge data sets, like tens of thousands, hundreds of thousands, even millions of images. And suddenly, you could actually take a neural network, give it a lot of representative images, and train all the weights. You'll be surprised. Some of the results that I will use tonight, it may look to you like they have a lot of parameters that need to be trained. Like, what is a lot? Like 1.6 million, right? And it may sound like a lot to you, but they are really tiny and small. Okay, ChatGPT uses how many? 250 billion, something like that, number of training. And then some of the more recent results that he's going to show you use about 650 million weights that they train. These are all neuron connections that have to be determined, right? So 1.6 million footprint really is very, very tiny network, okay? Just to put things in perspective. So, so what made that possible? Well, this is one of the slides we had to update from 2 years ago, because the thing that we had 2 years ago is ridiculous. I mean, people look at it and say, did you come from, like ice ages or something? NVIDIA is now doing, the 4090 at 100 teraflops, okay? But essentially, one is compute power. And, right now at RIT, we are just buying these A100s, NVIDIA A100s, that are about $20,000 each. And we have to buy 4 of them so that one student can run the training on that. Now, we don't have the budget, so we are going to someone else who has the budget, and that person is buying it for the lab. But I'm talking about that level of computation. And in fact, the presentation that Prasanna is going to give at the very end uses the image diffusion model. And the image diffusion model, which is very, very new, okay? His results are only a few months old. The image diffusion model really requires a lot of training time. And that's why you need these NVIDIA A100s, several of them in parallel running, just to get a decent time for training, okay? But when we talk about deep networks, we don't talk about 2 layers. We talk about 153 layers. We talk about at least 50 layers, right? And all of these are interconnected densely. So you have to essentially determine all of the interconnecting weights of the network so that it will do the analysis. It will do what you want it to do, okay? So, and then, I mean, I'm going to skip these, but another thing that is very important are the availability of data sets. These data sets are freely available on the internet. Anyone who wants to train something can go access them. But look, ImageNet has 14 million images, okay? The Microsoft Celeb has 10 million faces, in it, and so on. So just to give you an idea of the size of these networks. So let me, let me first set a paradigm here, okay? Because this is very important. And it's not obvious at first. When you do deep learning, there are 2 very different paradigms, okay? The paradigm that everyone is probably interested in is that I just got a picture, okay? Maybe, I even discovered it in my attic. It's old picture. I want to super resolve it, okay? I got it over the internet. I got it from family album or whatever. Can you make it look sharper, nicer, higher resolution? That's the paradigm everyone is interested in. And we will talk about that. In fact, the results that Prasanna is going to show are based on that, okay? And that's the first topic that I will talk about. But there is another paradigm, and that is called the task-aware paradigm. What does task-aware mean? In this case, you have control over creating a lower resolution image, okay? So I start with a high-resolution image. I have access to that. Okay, so it's not like I found this picture, in my attic. I have the high resolution picture. I have a method of creating a low resolution picture, which looks as good as the conventional filtering downsampling techniques in order to get that lower resolution image. But that lower resolution image has been made in a special way, okay? It has all of these things hidden in it that you cannot see. And it's truly a low resolution image. You will see an example of that. Then I make that accessible over the internet. I can transmit that very fast. I can store it, I can store many more of that resolution. I can transmit many more of that resolution than the original very high resolution. But every time that you want to look at it, you want to look at a higher resolution, you run it through a network. This is not a big network. It's about 1.6 million weights. So it easily fits on your phone. And, all you need to do is like push the button and say, show me this picture at a higher resolution. And what it does is that it takes this low resolution image, runs it through the network, doesn't have access to the high resolution one anymore, just take the low res and makes it much, much nicer and bigger, okay? So you will judge if that works or not. The results are very, very impressive. So I'm going to show you both paradigms. But let's start with the paradigm that everyone is interested in, namely the paradigm where you just come up with a picture randomly and you want to make it look nicer, right? So this uses what is known as the generative adversarial networks, okay, or GANs. GANs are rather new. Again, in that timeline, in the 40 years, they are 10 years ago, okay? And the guy who invented them is Ian Goodfellow, okay? Ian actually was a classmate with my son in college, so you know the Kevin Bacon degree of separation. My degree of separation from Ian is 2 because I have my son, and then my son was Ian's classmate. But anyway, he's a very important guy, okay? And he came up with this GAN. All the deep fakes that you see on the internet, they're all based on this generator the generative adversarial networks. And again, the purpose of tonight is not to go over what GAN is, but just the GAN works with kind of two networks, what we call a discriminator and a generator. And the generator will try to generate an image which looks like that deep fake. Okay, so imagine that you want to do a deep fake. You want to put somebody else's head on some other video and make it look very natural. So the generator network does that. Then you give it to the discriminator network. The discriminator network is trained to kind of call your fake and say, okay, it's fake because of this and this. And it gives it back to the generator network that learns from its mistakes, generates another round, which is a better fake. And then the discriminator has gotten smarter in the meantime as well. So it finds out and says, no, that's not good. And they keep going back and forth until the image becomes so good that the discriminator cannot tell the difference anymore. And that's how the training kind of takes place. Okay. So that's in a nutshell, like what these GANs are. And this is some example of the architecture. We are not interested in that. We're interested in looking at pictures, right? So, I mean, you could always, I put them for completeness so that anyone who wants to access the entire presentation, wants to actually, dive a little deeper, they could do that, okay? So, this GAN network, okay, is used, it's called SR, super resolution GAN. And the super resolution GAN essentially is used to upsample images by any factor that you want. You have to train the GAN to do that specific factor. Like you want to do a 2x factor, you want to do a 4x factor, okay? So this is a 4x demo. This is a low resolution image, okay? We happen to have the high resolution version of that because that's how we generated the low resolution image. So we can test how good the GAN is doing. This is the low resolution image. This is the GAN reconstructed high resolution version of it. And this is the original high resolution version of it. So you see that it's actually not that bad at all, which makes you wonder then, can this GAN really take any low resolution image and create something this impressive? Well, not quite, because the GAN has to be trained on certain class of images, okay? So if you, for example, train it on faces, then it will do really well on faces. But then if you feed into it a picture of text or, something else, it's not used to that because those 1.6 million weights that it got trained, they're really trained to work with kind of typical content that you want to see. So these are, there is a CVPR presentation. It's actually a nice presentation. Again, I give the website, so I just checked it. It's still there as of this afternoon. You could go to this website and you can listen to this presentation. It's a 12-minute presentation. And they usually do it to kind of show you the gist of the paper without getting too technical. So these are the pictures that I got from that presentation. And you could see that the SR GAN, I mean, they are comparing to other techniques. This is what you start with, okay? The state of the art, that is bicubic interpolation. It's better than linear interpolation, right? Bicubic interpolation will give you this. Still, you cannot really make out much. This is the state of the art as of the publication time of the paper. This is the results that they present in 2017. That's just over 5 years ago, okay? So it's not really that far back, although in the era of deep learning, 5 years is almost like my age. Okay, I mean, things change that much in a course of 5 years. So here is to show you some issues with it, okay, because that particular SR GAN was trained on faces, okay? Now, imagine that you take some text, okay? This is low resolution text, which has been 4x upsampled. So clearly bicubic is not really doing much. You can hardly read anything. So that's out of the question, but you wonder if you take your low resolution image and you feed it into this SR GAN, which has had its 1.6 million, weights trained on facial images, how well would it do? Well, this is what you get. This is the original, okay, in reference. And, you know, you might say, it's actually not that bad. I mean, this definitely looks better than that, right? But look, there are some parts of the text that are not reproduced that well, okay? So it's mixed results. Definitely better than traditional, you know, kind of bicubic. But if you train it on text, however, then it will start looking much better, okay? We don't have those results to show you, but that's something that you can do. So now, that was the first paradigm, right? As I said, that's the paradigm everyone is interested in. In other words, everyone is interested in taking a picture and, yeah, I want to make it higher resolution, okay? You use the SR-GAN. Actually, you probably use the diffusion model now, as of a few months ago, that Prasanna is going to show you in a few minutes. But then there is this other paradigm, which essentially says, I have control over the entire operation. I want to be disseminating low resolution images because they're easier to store, they're easier to transmit, but I want to be able to make these smaller images real big very quickly without having access to the original high resolution image, okay? That's the paradigm of the task-aware super resolution. Let's see how it works, okay? So this is an original image, okay? I will really demonstrate this mostly by just pictures to you, okay? And this is a low resolution image that we created from the high resolution image by simple filtering and downsampling. So nothing deep learning about it yet, okay? It's just you start with a high resolution image. I want to create a lower resolution image. Why do I have this here? Because later on, I'm going to start with this and I'm going to create a task-aware, kind of a controlled low-resolution image. And I'm going to put that next to this guy, and you cannot tell the difference visually, okay? So it's not that this task-aware low-resolution image is going to have, you know, some real weird things to it. No, it will look just like an ordinary low-resolution image, but the mathematical differences are subtle, but they're enough so that you can reconstruct a high-resolution image. Now, imagine you attempted to create the high resolution image using traditional techniques. By that, I mean you took this and you do a bicubic interpolation. Now, everyone can see, regardless of how far you are from the screen, that this image is not nearly as sharp as this image, right? So, you know, so far, nothing fancy. Now, I just want to show you again. Nothing, I didn't change anything. I just took away that. Now, I am going to change. See, I just changed this with a low resolution image that was done through the task-aware network. In case you did not see a difference, let me go back. Focus on this one, okay? Do you see a visual change in the image? It'll be tough to see, okay? So for all practical purposes, the task-aware low-resolution image looks just like the ordinary low-resolution image, okay? But now, imagine that I wanted to blow this up using the network, okay? Well, before I do the network, let's say I tried a bicubic interpolator. Still, same thing, right? Okay, but now let me try the task-aware neural network. Okay, so what exactly gave me this? What gave me this is this low-resolution image plus a network. How big is this network? About 1.6 million weights. But then this network will work on any image. Okay, so you take all images that you are, you know, you can come across, you run it through that same network with the same weights, as long as you have created this low resolution image through the actual network, you can always upsample it to a very nice looking image that looks high resolution. You could go even higher than 2x. Okay? So this is to show you that. Now imagine somebody took a regularly downsampled image, okay? If that person, you start with this is how we started. High resolution image, low resolution image. Now suppose they said, you know, I'm too lazy to create this low resolution image using the network. I'm just going to take any low resolution image, feed it through the network, and I bet you it'll work the same, right? No, it won't, because that's what you will get. Okay? Only if you feed the image that was created by the network to begin with into the network, then you will get that nice, sharp looking image. So how does this work? Okay. This is based on the concept of IRN networks. Okay. It'll become clear what that stands for, but these are reversible networks. I'll explain them in a moment. Let me show you the actual text example now. Okay, on that one. So this is a low resolution image we started with, and we upscaled it by 2x. So you see it's a little blurry, right? Because it was done using traditional techniques. And this is done using the IRN network. Okay? So you see that is much sharper. I think any aspect of it that you, even on the screen, you know, like you could still see a huge difference between this image, which is the one upscaled with the network, and this one, which is just upsampled using regular techniques. But, you know, the actual, and this is 4x. Okay? 4x is even more impressive, right? Because you could hardly read any of the text at 4x upsampling, and look at how visible all that is with the network. Okay? So I don't want to get into equations, as I said, but it is actually very interesting to see the paradigm that makes this happen. Okay? So the way that these networks work, as I said, we had IRN. It stands for invertible rescaling network. Okay? What is an invertible network? An invertible network is something that you could put something through it, and then you could run it backwards, and you will get exactly what you had before. Now, clearly, in order for that to happen, you can't really chop things off that image, right? Because you can't be throwing information away and then, you know, kind of recover it, right? You can't kind of pull yourself by, you know, pulling your hair and lift yourself that way, right? So the way that these networks work, and this is really fascinating, you start with a high resolution image, okay? You run it through the network, okay? You get the downscaled image. Now, clearly at this point, if you run this backwards, you will not be able to get mathematically identical original image, okay? It's just impossible. Mathematically, it's impossible, right? So what happens is that this network will decompose this image into 4 images, okay? So that overall the information is there. One of them is this low resolution image. It's kind of like wavelets for those of you who are familiar with that. It's not exactly wavelets, but similar to that. But then there are these 3 images that are stacked there, right? So the combination of these 3 images, which have a lot of information in them, high frequency information that is, and this image, if you take these back through the network, you will get your original image. Okay? The information is there mathematically. You will get it back exactly. And then, of course, you will say, well, you know, anyone can do that, right? I mean, if I were to take my original image and create this low resolution image, and then I have to carry this extra baggage of 3, you know, high frequency images, then of course, whenever I need it, I can put them together, right? Okay, but here is where the magic happens. The way that the magic happens is that, yes, if you put all these 4 images into the actual network, you will get your original image back. But we're not interested in getting our original image back, okay? What we are interested in is to get back an image. This is mathematically identical right now, okay? But we want to get something that, as far as visual inspection is concerned will feel just as high resolution as that. Does not have to be mathematically the same. And here is where the innovation in this network lies, okay? What they do, and I don't get into the details, of course, but the publication is right there. They take these 3 high-frequency images, which clearly depend on this and that, right? Because they are the 3 high-frequency images that accompany this particular image, right? It's this package that will mathematically give you this back identically, okay? But they have trained the network in such a way that they can replace these 3 high-resolution image-specific images with just random noise. And how do you generate random noise? You just have a random number generator. It generates random noise on demand. So this is what actually happens, okay? Right now, as I said, in the current way, this is mathematically identical to that. Okay, why? As I said, because this actually been decomposed. These are very specific, as you could see a little detail to this image, right? But now imagine I scrap those images. Okay, I scrap them. Okay, of course this will go away because I cannot get this back anymore, right? Once I scrap them, I cannot get back the original anymore, but I replace them with this random, I have a random number generator, literally, which generates Gaussian noise with a mean of 0 and a variance of 1. And I populate these images. They're nothing specific. I can always do it at the type of reconstruction, just generate random noise and put it in there. And then I combine that through the inversible network. And so essentially this is replaced with generic random generated data, which is not image specific, it's image agnostic, right? And so the case specific high frequency images are replaced with the case agnostic random generated images, and the output is still looking visually the same as what used to look mathematically the same, okay? The same principle, by the way, is used in the presentation that Prasanna is going to give in the image diffusion model. Essentially, what you do in the model that he's going to talk about, you will start with an image, and over 2,000 steps, you convert it into noise. But then you can take that noise, which you could actually generate randomly yourself, you don't need that image anymore, and combine it with a low resolution image and work your way back over the 2,000 steps and get a very nice high resolution image back. I know it kind of sounds weird, but you will see the results, okay?
This require classes of images to train the network, or does this work with all images? Or does it require still, again, that you use categories of images?
Well, that's a very good question, okay? Let me defer that question until I show you some results, because that's exactly what we did. Prasanna, at RIT, we have to take this qualifier, okay? And when you're in a PhD program. And the qualifier essentially means that you will pick a paper, you're given a choice of a few papers, you pick one of them, and you implement it, and then you come and make the presentation. This is Prasanna's PhD qualifier implementation. So he implemented this, in great detail, and then he started applying his own images, which were outside the training set and were outside, the overall category of images that it was trained with. And I have some results that I'm going to show you. Okay. So essentially, let's look at these images one more time now in light of what we've learned. You've got the original image, and this is a task-aware low-resolution image that has been formed by the network. And then all you have to do now, you take this, you generate random noise in place of those 3 images that were there. And then you take these 4 images, one of which you actually have, the other 3, you can generate anywhere on demand. And then you run it through the network, and you get this back. And this is just to tell you that it's a case agnostic random number. You're just generating a set of random numbers, really. It doesn't cost you anything, and then you get this back. Okay. Now, going back to Wayne's question, And by the way, if you try to again, I've shown you these images before, but if you try to use bicubic, you really will not get anything. Okay, so how does the actual reversible or invertible network work? It's right here. I'm going to skip the next few slides because they really were mostly for information purposes, but it just shows you how the network works. Okay, but here are this is detailed presentation that Prasanna made for his qualifier, and you probably want to see images, right? So I'm going to show you images, but I highlighted these two numbers because one important aspect of a neural network is its footprint. How many weights does it have? So when you train it, exactly how many numbers it is that you determine that characterizes that specific network, right? So depending on if you want to do a 2x upsampling or you want to do a 4x upsampling, the size of the network would be about 1.6 million weights or 4.3 million weights. And if you think those numbers are large, wait until you see the 250 and 650 million number of weights, okay? But then considering that you could practically take any image under the sun and run it through that network and, get a good result, these are not that bad. So here is an example that Prasanna used this, outside the training set or the test set that they had reported, and he did a few more. So this is an original image from this open image data set, okay? And then he did a 2x downsampling and then upsampling, or a 4x downsampling and upsampling, okay? And these are all done with the network. So when you have I'm not showing you the low resolution image here. I'm just showing you the low resolution image that has been upscaled by the network. But remember, this is the original image. This has the same size as the original image, but was reconstructed from an image which was half the size. And this was reconstructed from an image which was quarter of the size in each dimension. And you look at the actual license plate is probably where the information, and by the way, all of these, Prasanna has made them available to the public, so you could go and run. He has all the code, he has all the images, everything you can run for yourself. But this is the actual comparison. So if I took that low resolution image and I just used bicubic to upscale it, this is what the license plate would look like, okay? But when I use it with the network, this is what the license plate looks like, okay? And this is the original image. To me, it seems like this looks even better than the original image, but I'm not going to go that far, okay? So here is the end of my presentation. Now, as I said, Max Planck is going to take over, and he's going to do his name is Prasanna, actually. But he's going to talk about this the newest, which is what we added since this presentation was made. So the stuff that he's going to talk about is just a few months old.
So, hello everyone. I'll be talking about these latest technology in deep learning. They're called diffusion models. So they start from a random noise and iteratively refine it to get realistic looking images. I'll just play this video on the latest paper called Image Super Resolution via Iterative Refinement. So what's happening is it starts from random noise and slowly progresses to get us a super resolution image. These networks, as Dr. Rabbani said, are pretty huge. They range from 150 million parameters to 625 million parameters. And they take around 4 days to run on 64 TPUs, version 3. And not all of us can have access to that. Like this is by Google research team. So it's very fascinating to see that with just a few pixels of information in the eye, It is able to infer color, texture, and so on. So if you see the resolution, super resolution task here, it is from 64 to 1024, which is a pretty huge upscaling task, around 16 times. So this in fact is achieved by cascading two of these models. Each of these models do a 4x upscaling, and you have them back to back. So, and this is the paradigm of when you start with any image on the internet, you can use this to upscale it into the super resolution version. So I want to talk about this diffusion process and how it works. So first we start with our original image and we pollute it with noise. So over steps, we start adding noise to it. So the way the noise is added is through a Markov chain. So Markov chain is a chain of events in which your current state only depends on your previous states. So in this fashion, they add the noise. The noise is strategically added such that we can model the reverse process as well. So here is how they add the noise. So the idea is to add a noise in each iteration and completely destroy the image. While doing so, we also are interested in learning what the statistics of the noise that was added in each iteration. That's where the learning process or the neural network comes in. So let's say in a particular step, we added some certain noise that takes from yt minus 1 to yt. So we start with this noisy example along with our low resolution image. We first use a bicubic interpolation to bring it to the high resolution space. And then we concatenate these both together. So the low resolution image acts as a condition on these generative models. So, and then we send this information through our network. In this case, it's a UNet. And then we expect to produce the lesser noisy version of this input, which should be exactly the same. So here the learning is to train the network to learn what kind of noise that has been added and to remove it. So in the reverse direction, this is what happens. You start with the noise once the network is learned, and you have your, this image is conditioned on your low resolution image. Then you input this through that model, and it should generate a lesser noisy version. And you iteratively refine and improve your image until you get a final version that is very high resolution.
And how many steps are involved in this?
So the authors have chosen to use 2000 steps. So if you use the lesser number of steps, the network finds it hard to model the noise that has been added. And if you use too many steps, it takes longer to train. So you have to find a sweet spot. They've chosen 2000. And then here is what the UNet architecture look like. So it's called the UNet because of this change in resolution, which looks like a U. And they have a specific, so right here, it looks like a U because the resolution goes down and comes back to the original size. And you see different size upscaling tasks have a particular network. And the parameters go from 150 million to 625 million. In the first example that I showed you, we're trying to go from 64 to 1024 resolution. So it's basically a cascade of this network followed by this. Yeah. So here are the results from their paper. Here is a bicubic interpolation from 64 cross 64 to 512 cross 512. And here is the paper results. And here is the original one. I bet you can't make out the difference between the paper one and the original one unless you have a closer look, a zoomed in look. So we can also cascade these together. to get a very super high resolution image by having several SR3 modules in series, and they should be able to generate very high definition images. So yeah, that's all I have.
So if you have any questions on any of the techniques that we covered tonight or access to Prasanna's code, feel free to contact us. I assume that there will be a copy of our presentation posted somewhere so that you could actually access all those websites and the cited papers. And thank you all for being here tonight. We are really honored.
Thank you all.
Any questions?
You said it was 54 computers for 4 days?
Yes.
That's on 1,000?
Yes, steps. So 64 computers, they have TPUs, version 3 TPUs. Because this is Google, they have access to that. And it takes 4 days to train.
So where do you see the application?
I mean, so these are pretty popular now. If you know about DALL-E, so you give any text prompt and it should create really high realistic looking images. So this diffusion model is currently like the boom in deep learning. It has several applications.
Prasanna, is this diffusion model the same one used, for example, in ChatGPT in order to create, these realistic images? Or
Oh yes. So yep, OpenAI, they have ChatGPT for their text language models, and also they have these image generation based on these exact diffusion models.
And they're used for music as well, right?
Yep, they can generate audio. They can generate. So the
Bruce
applications
would
are
be
pretty
interested in that, right? They can't do it as good as you do, Bruce, but
Yes,
So
go ahead.
you start with the 60 by 60, 64 by 64 image. That's a pretty clean image, right?
Mhm.
If you had an old VHS tape and you had a face that size, and tried this technique, what would it look like? Would it be as clean as that, or with the noise and all that's really what the quality of your?
So it should do a very good job in increasing the resolution. So if you feel you have a lot of noise in your, let's say, image, you can actually downsample it and give it to the network, and it should do a better job in giving you the upsampled version without noise. So all these convolution networks, they generally like remove noise inherently. So they should do a good job for removing the noise.
But what if it was an old image
Mhm.
from tape or something, and all you had was the noisy 64? What would that? Would you get something that looked pretty much like a face, or would you?
Maybe. So this is pretty good with faces. So they've I've seen another research where they try to add noise in the input, but still the high resolution version does not have any noise because it's trained like that.
Yeah. Ken, actually, Prasanna also worked on noise reduction. And, when I say work, this work has been done mainly, but he implemented a lot of these noise reduction techniques. We didn't talk about that. We only focused on super resolution. But these networks are also used for denoising.
Process.
Yeah. And as he said, you could start with this image and then you could remove noise or reduce noise by going to a lower resolution image through binning or averaging. And then we could actually do the upscaling with these networks, and you will get a nicer image than even at that same resolution where you started from, than you had.
I get where you're going with this, Ken. The VHS images the chroma and the chroma bleed and stuff that happens. There's all these ugly things that happen on videotape that if we could recover those things, that would really, because a lot of us older people have our memories on those older. They're not digital. Yeah, that'd be very interesting to see if there was a way to take, not in general Gaussian noise, but very specific, some of the nasties that happen in the videotape.
Yeah. I mean, there's probably a pretty good business. You could do it efficiently for the same. People have a business of converting all Super 8 movies to optically. That's between all the families of VHS tapes.
I was going to say also, only the noise reduction, but also you were alluding to compression, obviously. And so is that a current that seemed like a natural one since you brought that up.
Actually, you started your work in the
Yes.
context of compression.
So
So is that likely to be commonly used, or is it currently commonly used?
so they use the same cascade concept to try to do compression. If you remember from that IRN network, it goes down to low resolution and you just discard the high frequency. So you can do a cascade and literally you can do like 16 times compression and try to get back a reasonable image.
Right, alluding to the simple the reconstruction of the random fields. So that seems like
the thing that we didn't emphasize here also, when you look at the reconstructed ones, the high resolution ones that look really good, if you actually look at the signal to noise ratio, which is kind of, the difference between that and the original, the SNR is not that much better than when you do a bicubic, for example, interpolation. But the visual content is just so much better, right? So, and that's another thing to say that mean squared error, which is what we traditionally use as a way of quantifying, the difference between two images, is not really a good metric because
it's additionally impressive, which I didn't hear any visual weighting as part of the
yeah,
algorithm.
no, it's not.
Right. That's not there, but clearly that's very effective.
Yeah, that's a good point.
So yeah.
So any technique in IRN down or away the three other images, and the compression is applied. Value or something. What is it when it's again with that?
Networks are highly sensitive to the exact image that it created. So any artifacts that you created will amplify and show in your output image. So if you want to get really good results, you need to have the exact same image that the IRN network generate.
And we haven't tested it, okay? But I think that his statement is just because I showed you that when you use two images which are so visually close together, right? One is just a downsampled version with, let's say, a cubic, and the other one is a downsampled version with a network. And you put those two small images next to one another, they look almost identical, right? But when you reconstruct the higher resolution image from the bicubic one, it doesn't look good. But when you reconstruct it from the networked one, it looks great. So I would suspect that, even though we haven't tried it, but JPEG will produce the same kind of noise. And as Prasanna said, it's very sensitive to that. So the idea here, though, is that you could take these images and essentially downsample them to a size that is easy to store without having to do compression on them and disseminate, share. But depending on what resolution you want to view them as, you just run them through the network.
Yeah,
I'm just curious. You said in the reconstruction process, you load it with.
We make sure that the high frequency try to resemble
is
a Gaussian
that
distribution.
generally the statistics of discarded images?
That's the total idea. We try to force the yes. So we make sure that the high frequency then we replace try to resemble a Gaussian distribution. So yeah, that's the total idea. We try to force the high frequency to look like Gaussian, and then we replace that with a Gaussian distribution.
Would it be appropriate, as Rick's going back to the discussion, so you got your JPEG image, right? So your 8 by 8 blocks have these different, line pairs, and it looks very noisy. Would it be appropriate, as Rick's question, to run that through, or should it be better to blur it first?
So you're saying the downsampled version has gone through
64-bit
JPEG artifacts.
of line pairs and stuff in your image.
So you're saying the downsampled version has gone through JPEG artifacts. Blur it before. That's what I feel intuitively as well.
One term and up to your 8 by 8 experience. You can see those in the text. It might be better to
Blur it before. That's what I feel intuitively as well.
You don't have experience. The two different downsampled versions, like visually, but if you difference them, what would you? Is it just random noise?
I think there's some edges might pop up a little bit.
Higher contrast.
Yes.
So you're dealing with color images.
Mhm.
Are you treating it as RGB? And treating each of the channels independently, or you have them components?
No. So we just input the raw image, and the network is built to like see it across all the colors as well.
Yeah, the network
So-
works on RGB.
Hmm?
It's not our network. That's the published network works on RGB.
Okay.
So there might be opportunities of maybe working in a different color space or different representation. But the network is really color agnostic. It just says these are three images, you know.
Three independent.
Exactly.
RGB.
And it just works. So it might as well work with grayscale or work with three grayscale.
Right, okay.
Same.